Welcome to Visual Algebra Lecture 2.7, Dicyclic and Diquaternion Groups. In this lecture, I will show you two families of groups that can be constructed by generalizing the quaternions. The dicyclic groups result from replacing I, a fourth root of unity, in Q8 with a larger nth root of unity. When n is a power of 2, we get the generalized quaternion groups. The diquaternion groups result from adding a reflection to a quaternion group. This is easiest to make concrete via our standard matrix representation. Both of these constructions and the groups in the subsequent lecture are covered in my recent American Mathematical Monthly article, Dihedralizing the Quaternions, so I encourage you to check that out. Let's start by reviewing the quaternion group Q8, which we saw in Chapter 1. This has 8 elements, 1, I, j, k, and their negatives. And for this lecture, I want you to think about I as a fourth root of unity in the complex plane. So in the unit circle, remember that lies up here. And we write that as zeta 4, or as e to the 2 pi I over 4. It's a 90-degree rotation in the counterclockwise direction. And then j is just an abstract imaginary number, and we know that I times j equals k. So the quaternion group is generated by this I and j. We often throw in k, but we don't need to. And the matrix representations of these elements are, I is given by R4, which is the complex rotation matrix, Rn for n equals 4. Here's the fourth root of unity zeta and zeta bar. J is represented by this matrix here of order 4, and then R times S, or I times j, is this matrix here. The dihedral group is generated by an nth root of unity, just a 2 pi over n rotation, which we can think of as zeta n, or e to the 2 pi I over n, and a reflection f. We can also represent these with 2 by 2 matrices, where the rotation is represented by this matrix, Rn, where the diagonal elements are zeta n and zeta n bar, and the reflection is the complex reflection matrix F. Here is a Cayley graph for Q8, and here is a Cayley graph for D6. So in this lecture, I'm going to generalize Q8 two different ways. And first, I will replace this matrix here with a matrix Rn, in other words, replacing a fourth root of unity with a larger nth root of unity to get the family of dicyclic groups. And then I'll start with Q8, and I will throw in a reflection matrix to get a larger group, and that's what I like to call dihedralizing the quaternions. Okay. When n is even, I'll discuss the odd case shortly, we can replace I, which is zeta 4, with a larger nth root of unity to get the dicyclic group. So I write this as dic n, and this is generated by zeta n and j, which is more concrete in matrix form. That is by this matrix, Rn, and the matrix for j, which I've called S. And a presentation for this is as follows. It's generated by R and S, where R to the n is the identity. This is an n-fold rotation. S to the fourth is the identity. This is like j. J squared is -1. And then we need these two other relations. So RSR equals S. We've seen this little motif before. RSR equals S. It also came up in the dihedral group. But also we need R to the n over 2 equals S squared. And I want you to think about S squared as -1. So that's like J squared. So this is saying that if you take an nth root of unity and you raise it to the n over 2th power, then you get -1. This is one reason why we want n to be even. So here's a Cayley graph for dic6. And let me just mention that the multiplication rules for I times j are they remain unchanged, because if we do this for n equals 6, then zeta 6 is 1/2 plus root 3 over 2 I. So that's what it is in Cartesian coordinates. If this is the unit circle right here, it sits right there. So this times j on the right is 1/2 j plus root 3 over 2 k. So in this Cayley graph, this is my favorite of the two. As you go around the outer ring, you increase by powers of zeta. So this is zeta squared, zeta cubed, zeta to the fourth, zeta to the fifth, and then when you go inward, you get you get j. So this is j, this is zeta j, this is zeta squared j, zeta cubed j, zeta to the fourth j, and so forth. Now, if we make all these four cycles, what's the word, concentric, we untangle this, we get a diagram like this. And here, if you go inward, you get powers of zeta. And if you go around this way, you get powers of j. So this is 1 zeta squared. Notice that, I'm calling this -1 instead of, this could be zeta cubed and zeta to the fourth. But for this purpose, if we think of this as 1 zeta squared, then going around in this direction are powers of j. So these all have a j in it. These all have a j squared or a -1 in it, and these all have a j cubed or -j in it. Several comments about this. First of all, we know what the order of the elements around the outside are because we understand the roots of unity, but I claim that all of the elements in the inside have order 4. The square of any of them is -1. Maybe it's not as, I think it's easier to see that over here. So these are the roots of unity along the x-axis, but along here, I claim these have order 4. So if you go blue, blue, -1. If you go, this element is red, blue, -1. This element is red, red, blue, -1. And similarly down here, you can red, red, backwards, blue, red, backwards, blue. All of these things have order 4. And as we do larger n, so if n equals 10, you can imagine that this diagram is going to look the same, except instead of 6-fold symmetry, we're going to have 10-fold symmetry here. And if we have n equals 10 over here, we're still going to have this 4-fold symmetry. We're just going to have 5 rings instead of 3. Now, let me say one more thing about when n is even. We can define this when n is odd the same way. So if I try to define dic3 as being generated by zeta 3 and j, what that is that's the group that is generated by, here's zeta 3 right there. Let me actually write that out in zeta 3, which is, sorry, my zetas are terrible, zeta 6 squared. And then j, of course, is right here. So I claim that these two elements actually generate all of dic6. And to see that, well, when we have j, we can follow the blue arrows. We have these 4 elements. We have zeta 3, that's here. And now if we follow j, we have all of these elements. And then you multiply by zeta 3 again, you get down here. And now you have all of these elements, so you get all of the elements. So in general, if you have an odd root of unity and you're allowed to reflect, then you can also get the corresponding root of unity that's for twice, that's just twice as much, which is the reflection across the complex axis. So dic6 is really just dic3. And so it's not wrong to define this for odd n, but we don't get anything different. So we might as well just only use this definition when n is even, so we don't double up. I also want to mention that my name for this group, dic(n), is non-standard. Most books, and by most I mean pretty much all books that I've seen, will call this group either dic3 or dic12. Dic12 is because it's the dicyclic group of order 12, and dic3 is because it is the so-called third dicyclic group. And I don't like this notation, dic12. I think it's much better to have the subscript n to note what the nth root of unity is. I mean, this n should match this n. But Ironically, the reason why there's the di prefix in this group is because when this notation is used, so if we were to call this group dic3, then it would be the case that C6 is a subgroup of dic3, and this thing being twice that, being a factor of 2, is where the di prefix comes from. So ironically, if I use this convention and force the prefix to be match the root of unity, then the whole reason for calling these dicyclic groups goes out the window. But I'm okay with that. The dicyclic name already sticks around. I hope this catches. I think it's a losing battle, but I really hope this catches on. And if you ever talk about these groups, I hope you use my convention, because it really does make the most sense with the roots of unity. Here are some more Cayley graphs of dicyclic groups. This first one is dic4, but I will always call it Q8. This looks just like the Cayley graph that we've seen before, except the colors red and blue are switched. So this is J and this is I. And this really highlights the fact that I and J are essentially the same element. They play the same role. Formally, this means that there's an automorphism sending I to J. But I'm using this because this is that form of the Cayley graph that we saw in the previous slide. And so here is that graph that we did see. This is dic6, and this is dic8, which I will always call Q16. And I'll talk about this soon, but when the subscript is the power of 2, the dicyclic group is a generalized quaternion group, and we say that because it shares certain properties of the standard quaternion group that the other dicyclic groups do not. So down here are the cycle graphs of these three groups, and what I want you to notice is in the quaternion group, all 6 of these elements have order 4. So there's a red 4 cycle, a blue 4 cycle, and then this orbit of size 4 generated by K. But then for dic6, what happens is we replace this red cycle of the 4th root of unities with a 6th cycle consisting of the 6 roots of unity. But all of the other elements have order 4. So they are all contained in size 4 orbits. Remember that? These are the ones that are on that inner cycle, or in this picture, are on this vertical line. Over here, we have a length 8 orbit, and then everything else is in an orbit of size 4. One reason I like cycle graphs is because they clearly show this pattern that I don't think is apparent at all from Cayley graphs. And as we compare groups, as we compare dicyclic groups to dihedral groups, to groups that we will see in the next lecture, semi-dihedral and semi-abelian, it helps to see their Cayley graphs. But there's a lot of different Cayley graphs depending on choices of generator. And as we've seen, cycle graphs are not unique, but there aren't as many of them. And I think in these cases, there's really only one of them. And it highlights structures, both similarities and differences across groups that the Cayley graphs just do not. In chapter 1, when I introduced the quaternion group, I think that's in the lecture on Cayley tables, I showed you how there was a quotient of it by constructing a Cayley table where I arranged the elements in a certain order. So when you squint your eyes, you see a Cayley table for V4. So here it is for here. We can do a similar construction for dicyclic groups. And to motivate how this is going to go, I want to remind you that V4 is really just the dihedral group D2. I think I discussed this in the lecture on dihedral groups, because it's generated by R and F, with R squared being 1, F squared being 1, and RFR equals F. That is the Klein 4 group. The quotient of the dicyclic group dic6 by the subgroup containing 1 and -1 is isomorphic to D3. Here is a Cayley table, and here is a Cayley graph. The product of plus or minus zeta j, that's this element, with plus or minus zeta squared j, that's this element, being plus or minus zeta squared, just means that if I take any element in this set, plus or minus zeta j, with any element in this set, plus or minus zeta squared j, then I get one of the elements in this set, either plus or minus zeta squared. More generally, it will hold that the quotient of the dicyclic group by the subgroup generated by -1 is a dihedral group of half the size. So that is dn over 2. I don't have a way to prove it now, but we will understand it better when we study homomorphisms and when we see the subgroup lattices of these groups. As I mentioned earlier, when n is a power of 2, then the dicyclic group is called a generalized quaternion group, and we use the subscript to match the order of that. So dic 2 to the n minus 1 is the group q 2 to the n. As we'll see, especially in later chapters, a reason for singling out these dicyclic groups as generalized quaternions is because they contain certain properties that general dicyclic groups lack, that the quaternion groups, Q8, have. And much of this boils down to the following fact, that in a generalized quaternion group, Q2n, or dic n, when n is a power of 2, every non-trivial orbit contains r to the n over 2, which is -1. So here are 3 examples, and -1 is this element over here. And we've already discussed that all of the elements along this vertical line have order 4 because their square is -1. So we know that all of the orbits that contain these contain a -1, or orbits generated by these. But now let's talk about the ones along the outer ring. So these are just the roots of unity. And I think it's best to see it with an example. So if we have r here, the orbit that contains this is just everything. If you have r squared, then and you multiply this by itself, you get -1, r to the 6th, etc. Even r cubed, multiply this by itself, you get r to the 6th, r to the 1st, and then r to the 4th. And every single one of these, if you start there and you just multiply by itself, you'll get to -1 before you get to 1. And that's because n is a power of 2. What this means is that every subgroup, every non-trivial subgroup contains -1, and this has far-reaching implications. In particular, it means that these generalized quaternion groups do not decompose as a semi-direct product of its subgroups. And that's something that we won't understand until chapter 4. And that's, I think, all I want to say about the dicyclic groups. It's worth mentioning that before I started writing my book, I had heard of these. I didn't really know what they were. I had seen the obscure presentation that I showed you earlier. And talking to my colleagues who also teach algebra, they pretty much have the same reaction. They're like, yeah, I've heard of that. I don't really know what it is. And certainly none of them knew them as the construction that I just showed you, which is replacing I with a larger root of unity in the dicyclic group. I certainly didn't know that. And when I heard about that, my reaction was, why didn't I think about that earlier, like years ago? And that seems to be a common reaction. So part of my reason for including these is because I want to publicize these groups. They are important. They are great examples, and they really come to life with these Cayley graphs in a way that they just do not with those presentations like I showed you earlier. Now it's time for our second construction. And for this, let's take our standard representations of the quaternion group Q8, here they are, and the dihedral group Dn, generated by Rn and F. And let's think about what happens if we take a reflection, that is, take this matrix and we throw it into this group. So we include it as a generator. This is called the Pauli group on one qubit, named after physicist Wolfgang Pauli. And I will call it the diquaternion group because it's really just the quaternion group with a reflection added in. If you look it up online, you might see that it's generated by 3 matrices, X, Y, and Z, and it contains 16 matrices, these 3 and the identity, and then what you get by multiplying these by plus or minus 1 and plus or minus I. These matrices are called the Pauli matrices from quantum mechanics and information theory. And X is this reflection matrix right here. Y is I times this matrix for J, and then Z, what is Z? Z is like this matrix I times, I think, negative I. I don't know too much about these. These somehow represent spins or half spins, but I've talked to physicists and they say, oh yeah, this means a lot in quantum physics, and I don't really know why or how. It's easy to check that X times Y is this matrix R for I. X times Z is this matrix S, which is really for J, and then Y times Z is T bar, which is negative K. This group can be constructed in other ways as well. Namely, it is a semidirect product of Q8 with C2, with D4 with C2, and C4 cross C2 with C2. You'll see what semidirect products are intuitively in a couple lectures later in this section, and then formally and rigorously in chapter 4. It's also a semidirect product of C4 and D4. Notice that this group has order 4, this one has order 8, and 8 times 4 is not 16, the size of this group, but 32. It's because a central product is like a direct product, but there's some overlap in these factors, namely they intersect in elements that commute with everything, hence the word central. I should say that this group is also a central product of C4 with Q8. I didn't write that down. In the previous lecture, I talked about the website Wed's List, and I showed you a bunch of really beautiful pictures of Cayley graphs that were built on Archimedean solids. This website is written by mathematical hobbyist Nick Webb, and it's got a whole bunch of really cool pictures and visuals, and I encourage you to check it out. He has an entire page devoted to the Pauli group, and he writes, among the groups of order less than 32, the Pauli group is one of the hardest to understand. It can be regarded as any of these 3 semidirect products, which means that it has these 3 groups as normal subgroups, something that you'll learn about in the next chapter. Then he says, I don't know about my readers, but I find that hard to envisage. This page aims to make the structure of the Pauli group easier to understand. And then he has some pictures and some explanations of it. But he doesn't say anything about this. I don't think he knew about this. And so I emailed him. And I sent him my paper, Dihedralizing the Quaternions, and he told me he enjoyed reading it. It is a new way to do this that I have never seen before. And I didn't have a name for this group for a while until December of 2021 when I came up with the word diquaternion, because that really is what this group is, dihedralizing the quaternions. Here is a Cayley graph of the diquaternion group and a presentation. It's generated by X, Y, and Z. So this is X, which is the reflection matrix F. This is Y, and then Z is here. And all of these have order 2, and XY has order 4. So XY goes up here. That has order 4. And then XY is central. It commutes with Z. So XY times Z equals Z times XY. Now, let's think about what we notice about this. First of all, I've highlighted the quaternion group, a subgroup, in yellow. If you look at the matrices along this outer ring, you might recognize this Cayley graph. This is the dihedral group, D4. We saw this in the first few lectures, generated by 2 adjacent reflections. And then also, since XY commutes with everything, it commutes with Z, then this element and that element generate this subgroup of these 8 elements. And this is an abelian group, and it's C4 cross C2. It does not have an element of order 8, so it's not cyclic, and it has an element of order 4. The diquaternion group is usually generated with Pauli matrices, because that's usually what it's called. We can also write it as being generated by the matrices R, S, T, and F. Remember, those are the matrices the matrices for I, J, K, and F. Of course, we don't need F if we have I and J, but it's nice to keep it. Where Q8 is generated by R, S, and T, and dn is generated by Rn and F. So here are two Cayley graphs of the diquaternion group labeled in this one by the Pauli matrices and the identity element, and then the negatives of those and the products of plus and minus I times those. And then over here, it is labeled by R, S, and T. And then I have F here, but remember F is just the same matrix as the Pauli matrix F. Let me ask you a question. What do you think the quotient of this group by plus and minus -1 will be? Now, I haven't formally defined quotient, but I've showed it to you with the quaternion group and the dicyclic groups. What this really means is that we are declaring every element to be the same as its negative. So these are the same, those are the same, these are the same, etc. And one way you can answer this is construct a table. Let me give you a hint. I have my students do this. So let's do plus or minus I, plus or minus, that's I, plus or minus X, plus or minus Y, plus or minus Z, and then like this, plus or minus X, plus or minus Y, plus or minus Z. And see what happens when you multiply one of the Y's by one of the Z's. So if you do that, you get, let's see, red times blue. What you get red, blue, you get, so what you get down here is plus or minus I times Z. You get negative IZ. So notice if you do it, if you do negative, I claim if you do negative X times positive Y, or negative X times negative Y, you're going to get either IZ or minus IZ. Now, this is not always going to work, but I claim that in this case it does, and I want to ask you, what is this group? And if you construct this table, it'll be an 8 by 8 Cayley table, and there's only 3 abelian groups of order 8. There's either C8, or C4 cross C2, or C2 cross C2 cross C2. And one way to figure out which one this is to look at the elements on the diagonal and say, how many times does the identity element occur? In C8, there are only 2 elements whose square is the identity. You have 1 squared and r to the 4th squared is the identity. In C2 cross C2 cross C2, every element, the square of every element is the identity. So you'll have the identity element at every single entry on this diagonal. And then C4 cross C2, I think there's something in between. I think the square of 4 elements are the identity. So if you fill out this table and you just look at how many identity elements are on the diagonal, that is plus or minus i's, that will tell you which of these groups is the quotient. That is an exercise that is worth doing. And again, I assign this for homework in my class. Here are 2 cycle graphs for the diquaternion group. And I want you to compare and contrast how these differ from both the quaternion group and the dihedral group. So the quaternion group I've highlighted in yellow. Remember that those were just all 4 cycles. All the orbits were 4 cycles, the maximal orbits. And then for the dihedral group, remember we had, let's take D4. So we had a 4 cycle, and then we had 4 elements that have order 2, which are the reflections. So this kind of has features of both of those, and that should not be too surprising because we know that this contains both D4 and Q8 as subgroups. So I don't know if you prefer this labeling or this labeling. I'm on the fence. I think I slightly like this one, but this helps because it really does show how the reflection factors in comparison to just the standard quaternion group. Let me ask you a question. Do you see a way to generalize this further? What do you think? Pause this lecture. Take a few moments to think about it. What if we use a different root of unity, like we did with the dicyclic groups? It turns out that if n is a power of 2, and we replace I, which is zeta 4, or e to the 2i over 4, with a larger root of unity, but it has to be a power of 2, we get something called the generalized diquaternion group, or I call it the generalized diquaternion group. It's basically the generalized quaternion group, which are generated by these matrices with a reflection thrown in. It also ends up being a semi-direct product that I'll talk about later. And here's a Cayley graph. Once again, in yellow, I've highlighted the elements of the generalized quaternion group. The elements along the outside, this ring, forms a group isomorphic to D8, generated by 2 reflections. And also, as before, if you take, how do I want to say this? Let me just take a color. I don't know which one to use. If you take all of the elements that are on every other line, then you get an abelian group. So in this case, you get C8 cross C2. And this construction, again, generalizes for any n that's a power of 2. So you can start with any generalized diquaternion group and throw in a reflection matrix to get a group twice as big. Okay, so a natural question you should be asking is, why this requirement? Why do we need n to be a power of 2? And, well, you don't. You can define this group for any n, and it's a fun exercise to see what happens if you do this for n equals 6. So if you take the dicyclic group that with 12 elements and we throw in this matrix, what happens? I did not know this. I assigned this, I literally did not know the answer, so I assigned it as homework for my undergraduate class. And they came back and they said it's a group of order 24. I think it's like the special linear group S3 or SL2Z3, if you know what that means. We'll see that at the end of this lecture. But basically, this pattern breaks down, and I don't know what the general pattern is. I don't know what happens if you do this for n equals, let's stick with even numbers now, n equals 10 or n equals 14. But this is one motivation for why the dicyclic groups are special when n is a power of 2. Now, these things also break up as semi-direct products and central products in a very predictable way, like the DQ8. As far as I know, this family of groups does not have another name other than the fact that it can be written as like a central product or a semi-direct product. I've looked for it, but the term diquaternion seems to be new, and I don't see any other family that matches this. Something that's close is, I said that the original one was the Pauli group on 1 qubit. There is something as the Pauli group on n qubits. So the Pauli group on n qubits, how do you spell qubits? Qubit, yes, has order 4 to the n plus 1. So that means that the Pauli group on 2 qubits, if I want to write it as Pauli 2, has order 64. So this is not a Pauli group. So there is a generalized family of Pauli groups. This is not one of them. And then the Pauli group on 3 qubits is going to have order 256, and then it goes 1024, and then 4096. Whereas every power of 2 has a generalized diquaternion group. So let me know if you know of this group from somewhere else. I'm sure it comes up in some place. Like this comes up in quantum physics. Someone has played with these. I don't know how to search for them, but I really like the term diquaternion. I hope it sticks. I want to finish with a fun puzzle that I don't know the answer to because I've never really bothered to sit down and answer it. I think I could do it in a few minutes. But it's fun to not know. So, if you want to, you can answer this in the comments. On the left is a Cayley graph for the diquaternion group. And on the right is what I get by reversing the colors of these inner edges. So let me ask you, what group is this? Well, first of all, is it a group? Now, we saw that weird Peterson graph example in lecture 1.6, and maybe this is not actually the Cayley graph of a group. I think it actually is, but if it is, I claim that it's not isomorphic to this one. Do you see why? Here's one way to see it. Every element in here has order 1, 2, or 4. But over here, consider the blue-green path. So what's the order of this element? Let me call this G. So blue, green, blue, green, blue, green, blue, green. It took us 4 steps to get back here. So this is going to have order 8. Notice blue, green, blue, green, blue, green, blue, green. So this element has order 8, which means that if this is a group, it contains C8 as a subgroup, which the Pauli group, or the diquaternion group, I caught myself there, does not. Now you can go on LMFDB. Remember, LMFDB is this wonderful group database where you can search for groups, and you can search for all groups of order 16 that are non-abelian. This one is definitely non-abelian. That has C8 as a subgroup and has, well, look here, this thing has D4 as a subgroup. And let me think. I think it probably has, well, I don't know if it has Q8 as a sub. I'm not really sure. It probably does not have Q8 as a subgroup. But that right there should narrow it down to a handful of groups, if not only one group. So what group is this? Go answer that. And if you're one of the early ones to watch this video, you might be the first person ever to discover the answer to this question. And while you're at it, let me ask you one more. Here is a Cayley graph of DQ16. And if you reverse the colors of the inner edges, you get this one. And once again, this cannot be DQ16 because if you look at this element G generated by blue-green, let's see, you get blue-green, 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 blue-green. That's 4 steps. And then blue-green, 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 blue-green. That's 8 steps. So 8 steps to go around, and then it's going to take 8 steps to come back. This element here has order 16. So what is this, and how does this generalize? I think it should be clear how it generalizes to larger generalized diquaternion groups. But let me ask you one more question. Once you figure out what group it is, and I think it's a fairly straightforward exercise, figure out what generating set gives this Cayley graph. So like, what is this, and what is that? And label the nodes with this. And yeah, let me know if you do this in the comments. I'm looking forward to hearing about it. Okay, so that's the end of this lecture. In the next lecture, we're going to learn about another few families of groups that you can construct, well, this time by generalizing or tweaking not the quaternion group, but the dihedral groups. These are also in my same Math Monthly paper. It's a fun read. I encourage you to check that out as well. So coming up next are the semi-dihedral groups and the semi-abelian groups. So stick around and learn about those. See you then.